Let us discuss this reaction. So this is something to do to SN2 reactivity rate of SN2. So I have a compound CH3CH2Br, that is ethyl bromide. Let us call this compound is 1. If I do SN2 reaction on this compound, it will happen because the carbon that is connected to the leaving group is 1 degree carbon. So this carbon is 1 degree carbon. Now I can have SN2 reaction. Let us say the rate for this is very high. Let us call this R0. So rate for this reaction is R0. So rate of reaction is high because we have a primary carbon. Now let us say another compound. If I have this compound, and this case, now this compound CH3 here I have hydrogen CH2Br. Now let us call this this is isobutyl bromide. You have 1, 2, 3, 4. So this is butane. If you have CH3 CH3, this unit is called iso unit. So you have isobutyl bromide. So this compound is isobutyl bromide. This also contains 1 degree carbon. So the bromine, that is leaving group, attached to the 1 degree carbon. This can again go to the SN2 reaction. But in this case, the SN2 rate is 10 times slower. So if the first case the rate is R0, in this case rate is R0 by 10. That is the 10 times slower. Are you getting? In this case, even though this is a primary carbon, this is also primary carbon. But in this case rate is R0 by 10 if the rate in this case is R0. Now the question is, why in case of 2 rate is so slow? Why this is 10 times slower than the 1? And the hint lies something related to a steric. So let us think for half a minute and then we'll discuss the solution. So you have to think in terms of sterics. Okay, let us see. So if you have this compound, now this carbon is alpha carbon, bromine attached to the carbon. So functional group or substituent attached to the carbon. That carbon is called alpha carbon. So this is alpha carbon, this is beta carbon. Now if you see the beta carbon, there are 2 CH3 group is attached. So if nucleophile comes from this side, basically nucleophile will attack on this carbon. It has to come on this carbon, but this will basically make a crowd. So this crowd will even retard the attack of the nucleophile from this side. So even at branching at beta carbon can decrease the rate of SN2 reaction. So this is happening. Branching at beta carbon decreases the rate of nucleophilic attack, and this is generally true. If you have a gamma carbon, this does not decreases rate as a lot. But if you have a beta carbon, so if you have a beta carbon, if you do branching at beta carbon, rate of SN2 reaction will decrease. This is the observed experimental fact because of the steric effect. Now see, and that's why in this case nucleophile will not attack, nucleophile will do elimination. It can take H plus from here and then this double bond and Br can go here. So in this case, not substitution will take place, elimination will start, E2 will start, because base can either attack. If it attacks, then it becomes nucleophile. If it takes hydrogen, then it becomes a base. So in this case, and that's why if both are treated with a strong base, the first compound first will give SN2 product because there is no alpha branching, beta branching. 2 will give the E2 product. Are you getting or not? In this case, it can take hydrogen and this goes here and Br can go. So I can have a double bond here. So in this case, substitution will not take place because of the branching. But elimination can take place. You can take H plus and this goes here and Br can lose. And that's why in the first case the chance of elimination is very low because the attack nucleophile can easily attack. So first case, this case, nucleophile can easily attack, but in this case nucleophile cannot easily attack. And that's why in the first case you will have SN2 product, but in the second case you will have E2 product. Are you getting? So this means if you make the branching more, the elimination product will be favored because nucleophile is not able to reach to the location. So branching always favors the elimination. Are you getting? So if you have a tertiary carbon, elimination is favored over the substitution. And that's why we in forming ether, we does not take alkyl halide tertiary, the same thing. You see, this sometimes we use, if I want to form ether, so the same concept is used in this case. If I want to form an ether, let us say I have CH3, H, CH3, and here I have Br. Let me take one CH3 more. Now I am thinking, if I take this O minus CH3, I am thinking what kind of reaction will take place. I am thinking substitution will take place. This will go here and this will go here, and finally I will get this product CH3, 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 OCH3. I am thinking something like this, but actually this will not the case because this is tertiary carbon. So in this case, nucleophilic substitution will not take place. Now elimination will be favored because this can also act as a base. OCH3 minus you have, so it can also act as a base. It can take a hydrogen, so you have a hydrogen here, and then CH3, CH3, and then you are Br. Are you getting? So what it can do is, it can take one proton from here, this bond goes here, and you can lose this Br minus. If you do something like this, you will have CH2 double bond CCH3, CH3. So in this case, you see elimination product will be favored. So if you want to have elimination product, you have to make branching. If you want substitution product, you don't have to make branching. Are you getting? So you just copy this one, and then we'll discuss the next part. So let us copy fast. So if you want to have substitution product, you don't have to have branching. If you want elimination product, of course, then you can do branching. Elimination will always favor the branching. Elimination is always favored by the branching. Let us copy this one. If all of you have copied, then I can go for the next problem. Let us discuss the next problem.